Hi. So now let's have a look at how we can use the Chvátal-Gomory procedure to devise a method for solving IP problems. Basically, not necessarily you need Chvátal-Gomory procedure to generate a cutting plane algorithm. A cutting plane algorithm is something more general. And it's based on this idea of iteratively solving relaxations. And from the solution of the relaxation, generate a valid inequality that comes from a family of inequalities F, using that is called the separation principle. So the separation principle is that it tells us the following. If X is not a feasible solution, then you can find a hyperplane that separates X and its set, right? And but notice that it posed in a very general way. We will see very shortly that we can. A special case of this is for example, using Chvátal-Gomory procedure to generate valid inequalities for IP. This is being posed in the most general way we can possibly think of. The main challenge with cutting planes is that whenever you think of a family of inequalities, so you can think about these family of inequalities being those that are generated based on structural information. I can give you an example. TSP, when we solve the traveling salesman problem as an assignment problem, which is a relaxation, we might find a subtour. That subtour can be cut out with a subtour elimination constraint. That is what we're having in mind when we think about this family X. So a family is the family of subcut, or subtour elimination constraints, or cuts that are generated. Think about subtours. So notice I'm solving a relaxation and generating inequalities from F. And the separation principle is that the hyperplane here is that cut, that constraint that is separating the solution that forms a subtour from the set of feasible solutions. So you can see that principle we described when we talked about, traveling salesman problem and said, well, we can solve it as an assignment problem. If you find a subtour, you add a constraint and solve again. That is a cutting plane algorithm. So this is how general this is, okay? Clearly, now this makes more sense now, I hope, with the example, is that typically, if you think of a problem in the family of cutting generating of a family inequalities you want to generate, there's typically so many of them that it's practically impossible to generate them all. But we do know that often is the case that you only need a few. And once again, TSP is an example. You can see that more often than not, you don't need to generate all subtour elimination constraints, but just those that you found in a way while solving your assignment problem. It might be so you can artificially generate an example where you need them all, but often or typically you don't really need them all. And that's the belief upon which cutting plane methods are based. And the method can be expressed by a pseudocode just like so. So you initialize, you find a family of algorithm, a family of inequalities, of valid inequalities will be the collection of those. Typically not possible to explicitly define, but define it only implicitly by this notion of giving a solution. You can use the separation principle to show that, that here is a valid inequality because it separates this infeasible solution. And here is kind of posed, XLP, thinking about this as being a solution for your relaxation, really. But we are posing this already in the context of LPs because that's where we're trying to go. So this family will be a family of cuts of invalid inequalities for a X set that is expressed like we've been doing with a polyhedral set intersected by integer points. Because then, the relaxation is just the LP relaxation, and the separation principle is trying to find that. So it's a solution that is separating the LP relaxation from between, it's separating the feasible and the feasible set X. And then what you go about, we added this constraint and carry on. So it's a similar principle to what is going on in the TSP with the subtour eliminations, but now what we're doing is our relaxations is just the LP relaxation. And if the LP relaxation is not feasible, we're trying to find a cut that separates the LP relaxation from the solution of the LP relaxation from the current set. Well, it's separating it from the set X. So it's doing, if you remember that picture we had in the beginning with our little set X there, and then we had our feasible region saying like so, and we're trying to find something that says separates the optimal of the LP relaxation, that could be say here, from the feasible set. Okay. So we add the constraint and carry on. So the challenging part, I guess, would be, so what is this and how do we derive those? So just a remark here is that this is step 4, is what we'll be calling the solving the separation problem, which, depending on what sort of family you're using and what sort of relaxation you're actually considering this, if it's instead of the LP relaxation, it can be really tricky. So because it means, you know, being able to find a hyperplane that separates the solution you have from the feasible set. And depending on the family of inequalities you're using, it might be so that you end up with a solution that is not integer, or even, you know, thinking up more generally, that is not feasible to your original integer problem. And the reason for that is just because it might be so that you chose a family of inequalities that they cannot generate a full representation of the convex hull. You can think of a family of valid inequalities as a subset of all multipliers possible to be derived. So a family is kind of looking at, they are working as a subset of U's. And because it's just a subset of U's, it might be such that in this subset, you don't have those that are required to finally, you know, to truly describe the convex hull of X. And if you can't, or if you can't describe the convex hull around where the optimal points should live, then you wouldn't find a feasible solution for the integer problem. Again, in the context of using linear relaxations, will be the family you're using to generate these valid inequalities not allowing you to reach this term, to find a relaxation with a solution that is integer. And that's basically, you know, it will be the case when the family might not describe the convex hull, or at least the part of the convex row in the region of optimality lives. And you might get a separation problem that is perhaps as hard to solve as the relaxations themselves, or even not solvable at all. You just simply can't find a solution for it. And depending on how your family of inequalities are defined in the context of your problem, it might be a challenge just to find an inequality that separates the current solution from the feasible set. But not everything is lost, to be honest. This actually sort of, you know, kind of consolation prize is actually one of the most powerful engines behind the solvers we use to solve integer and mixed integer programming problems. It turns out that solvers out there, they have a collection of families that they use to generate valid inequalities, and these families are known because of structure, you know, underlying structure of your problem. And once you exhaust your list of families that you can use to generate cuts, it might be so that you don't have a convex hull, you don't have an integer solution. But because you've been doing this exercise of over and over and over adding valid inequalities, so let me do a drawing again here. Suppose our feasible region is like so. I don't know, these are our points, and this was the original formulation we had. And then you went through all the families of valid inequalities you know. This notion of family inequalities, families of inequalities, will be clearer when we talk about, you know, actual MIP technology in lecture 11. So I'm gonna go through some of those that are, you know, famous and used by these. But basically, you can think of them as structural patterns that can be used to derive, you know, valid inequalities and efficiently solve a separation problem to then obtain the valid inequalities. But suppose you went through all the families you know, and then you end up, you know, you found, say, let me get a different color. You found, say, this inequality, you found this inequality, you found perhaps this inequality as well, but you can see that there is a misalignment. I drew this on purpose. There is a misalignment there. See, so you end up exhausted all your possibilities, and you end up with this XLP there. But if you look at this carefully, your original formulation in green was this polyhedral set. Let me not move lines. Was this polyhedral set here? And now you have this polyhedral set. And you can see that P2 is contained within P1. So what's, you know, this constellation price is actually a very good one. It means that you are left with a stronger formulation. So if your cutting plane method failed, the next step is, all right, this is my current formulation, let's branch and bound it. And that's the underlying principle behind all efficient solvers for mixed integer programs. Like we'll see in 2 lectures. But so this is, you know, sounds like an awful consolation prize, but actually it's a very good one. It's a very good thing that can be exploited. But it might be so that your cutting plane doesn't end up with solutions. Actually, the other way around is actually really nice. Sometimes it might be so that your cutting plane phase is capable of solving your problem in your MIP solver. That means that the cutting planes, you know, the cutting plane part of your solver actually was capable of finding a solution. So you don't do any branch and bound, and that's great because, you know, you don't have to go through the hassle of having to your LPs, you know, kind of doing, you know, whenever I think about branch and bound, what I think is these cell divisions things that you see in biology classes, you know, 1 becoming 2, 2 becoming 4, 4 becoming, you know, soon enough you have this horrible massive population of subproblems to deal with. If you don't have to go there, you can stop with, you know, just a single problem that you are adding a cut and resolving, adding a cut and resolving, adding a cut and resolving. We know how to make that efficiently already, in an efficient way. So that's actually good news if you can, but it's unfortunately not that often the case. But anyway, we'll see all that coming today. But so for LP-based cutting plane methods, the most famous one is basically using LP relaxations. That's why the sort of code before was, you know, giving this idea of LP relaxations as they mean the solution of the relaxation. And basically the challenge is then combining LP relaxations with a way to generate valid inequalities that successively make P closer to the convex hull of X. And the way to do so is to have the knowledge of families that can be, you know, if you wish, that allow us to generate cuts, which ultimately means ways of automating the process of setting reasonable use for the Chvátal-Gomory process. And then we'll talk about one Gomory fractional cutting plane method, but honestly, any given MIP solver nowadays that you see out there will have about a handful, perhaps a few tens a dozen of families that they use to try to generate valid cuts, valid inequalities. But let's look at the one that was just using Gomory fractional cutting planes. Basically, it sort of exploits the Chvátal-Gomory procedure when you generate Gomory fractional cutting planes, the Gomory fractional cuts. And the idea is that we're going to generate the CG inequalities cutting off fractional solutions of the LP relaxation. And we'll do this over and over and over again. All right. We'll stop here, and then in the next video, we'll go over how do you generate Gomory fractional cutting planes, how it connects with, the simplex method, and we'll look over on numerical example. So see you in the next video. Bye-bye.